right, let's take a look at today's lesson. Last time we just started optimization. We set up the problems, but we didn't go any farther than that. What we're going to do today is we're going to set them up again, and then we're going to continue on. Some of these are the same problems that we did in the last lesson. Like this first one is the same problem that we did in the last lesson. But let's set it up again, just as if we haven't seen it. Let's remind ourselves what the strategy is that we're going to be using. So we would draw a picture if it's applicable. We would write down what numbers we have, and also we would assign variables to the things that we wanted to find. We would write an equation that we want to optimize. If you remember, this one was the main equation. And we had other equations that were called helper equations, right? So we had this is what we want to optimize would be the main equation, and then we would have helper equations, which would help us get the variables down to 1. Remember, with optimization, we just want one variable. That's why we write your equation in terms of a single variable. This is where the helper equations come into effect, where we would get the equation down to one variable. Then we would do the process. Now, last time we just went 1 through 3. We did this much of it last time. Today we're going to just go through the whole process. We're going to do 1 through 3, and then we're going to do the calculus part. So the calculus technique, this would be, these optimization problems are absolute extrema. Do we remember what test we use for absolute extrema? Candidates test. Very nice. We would use the candidates test. And within the candidates test, we find the critical numbers and the endpoints, remember, and we just test them. That's kind of the process. Okay, so that's just an overview of the process. So let's start it again. Again, we did this one last time. If you recall, we looked at, it said closest. So we're wanting to, what do we want to do? If it's what we want closest, we're going to minimize. We're going to minimize, and we want closest, so that, if I could spell minimized. So that's really talking about distance, right? If you want to be close, you want to be close in distance. So the formula that we used for this was the distance formula, if you recall. So let's just write that out. Distance formula equals x1 minus x2 squared plus y1 minus y2 squared, which, we have that on the formula quiz. So yay. All right, so let's look. So, okay, I prefer to put this point in as my, this at the second part, like the x2, y2, because I would rather subtract a number than a function. So that's where I normally put the point. So let's kind of rewrite that. So, and we've got x minus 5 squared plus y minus 0 squared. And if you recall, last time we were like, well, that's great, but we have two variables. We have x and y, so we need to look for our helper equation. And the helper equation is this additional equation sitting right here. So our choice is to solve for y or solve for x. It's already solved for y, so why don't we just utilize it that way? So let's go ahead and sub that in. So our distance would be square root of x minus 5 squared plus, and then we're going to we're replacing the y with the square root of x. We're substituting the square root of x for y. And then if you recall, last time we went ahead and distributed in combined like terms and got it cleaned up and just ready to go. So it was, x squared minus 10x plus 25 plus x. And then it is x squared, what did that give us? X squared minus 9x plus 25. Now on this particular problem, the first one, we're going to go ahead and do this one without a calculator, but number 2 and 3, those two, we're going to utilize the calculator. Okay, so the first one, we're going to do non-calc. The second two, we're going to do calc. So what do? All right, we want to do candidates test. We really don't have endpoints. This is a strange problem where we don't have endpoints because it's just on the curve. I mean, what would our endpoints be? I don't know, I guess 0 to infinity, but that doesn't really help. So what we want to do is find our critical numbers. So we want to find our derivative. All right, so I'm going to go ahead and rewrite this to the 1/2, just so it's easier for us to think about the derivative. What rule would we use to take this derivative? Power rule and chain rule. Yeah, you got it. Power rule and chain rule. So d prime equals, so we bring the half down, we copy and paste, we subtract 1 from a half, and we get what? Negative a half. And then we chain it, right? The derivative of the inside, the derivative of x squared is 2x, and the derivative of negative 9x is negative 9. All right, now we're going to have to set it equal to 0 to find our critical number. So I'm going to clean it up a little bit, just algebraically clean it up a little bit. So we know that this portion right here would be in the numerator, and this portion right here would be in the denominator, right? This negative 1/2 would push this down. So we have 2x minus 9 over 2 times the square root of x squared minus 9x plus 25. So when we are finding critical numbers, if you recall, we set the numerator equal to 0 to get our stationary points, or where f prime is 0. We would set the denominator equal to 0 to get our singular points, or where f prime is undefined. Remember that? Okay, so that's what we're gonna do. We're gonna do 2x minus 9 is 0. So 2x is 9, so x is 9/2. That is our critical number. That's where f prime is 0. We just need to check to see if we have any undefineds here, if f prime is undefined. So since this is a quadratic, I'm going to just think about, remember with our formula, oh, I know y'all know the song, right? For a quadratic formula, I know you do. You don't need to sing it to me, but I know you do. You know the radical part of there, right? The b squared minus 4ac. I just want to see, I'm just going to do a check to see if this is worth our while. So b squared, so that would be 81 minus 4 times 1 times 25. Is that going to yield a positive or negative number? That's going to be a negative number. So what does that mean about the denominator? Is that ever going to be 0? No, that's not. So we don't have any of those kinds of critical numbers. So we don't need to worry about this would be imaginary. And since that is the only critical number, 9/2, and since we don't have endpoints, I mean, it's kind of like, oh gosh, I only have one number. It really is, that is the point that's closest. Now that's the x value of the point. So let's look back what they asked. They want the point on the graph that's closest. So is it just an x value going to be sufficient? No, I have to have x and y, right, for it to be what they're asking for. They're asking for the point on the graph. So how are we going to get our x value? Our y value. Plug it back in, absolutely. So we're going to plug it back in. So let's do that. So we've got y equals, that was square root of x, so square root of 9/2. Now, I would probably do square root of 9 and get 3 and then just leave it like that. We don't need to rationalize. There's really no reason to do that. They would be fine if you left it as a square root of 9/2. That'd be okay.
Back to the these for minus 4ac formula.
Yeah.
It's imaginary because it doesn't.
Oh, good question. No, it's imaginary because what's underneath here is negative. And so the square root of a negative number would be imaginary. Yeah, this is like a kind of a shortcut. Okay, I was cheating. It's a shortcut. Instead of just doing the whole quadratic formula, I know that if the number under here turns to be negative, then it isn't even worth doing it because it's going to be imaginary. So that was kind of a shortcut just to see if we needed to worry about that. Does that make sense?
Yes.
Okay. All right, so we've got our x and y. Now we need to restate it. So our point is 9/2, 3 root 2. And we need to say what they said. The point is, so we need to use their words. What point on the graph is closest? We're going to say the point closest is. So we can write down here. This is the point that is closest. All right. And that's our very first one. So we finished that out.
So you never actually found what the variable t was. It's just.
Oh, good question. Now, it depends on what they ask you. What if they said, what is the closest distance? Then what should we do? Yeah, then we should use and find D, right? Then we should find D. If they ask us for the closest distance that point is, but they asked us for what point is the closest. Does that make sense? So yes, it could be that we needed to find D, but in this particular case, they didn't want us to. Okay. This is one of the ways that we do optimization with distance. Yes, ma'am. Okay, are we good? Okay, here we go. So number 2, again, we set this one up last time, if you recall. We set it up last time, and we have our, the 2 towers are 30 feet apart, if you remember. We drew this little diagram. We've got our 2 towers. Remember, we had somewhere in between them, there's a stake in the ground. Oops. Okay, and let's see. So what did we do? We called this wire 1, and we called that wire 2. And what did we have? This was 28 feet high, and that was 12. We made the distance between the stake and this right side X. And since this distance was 30, remember y'all told me what to make this part? Remember that? It would have been 30 minus X. That was our diagram. Okay, and so we talked about the wire is going to be equal to wire 1 plus wire 2. Do you remember what formula we used to come up with an expression for wire 1 and wire 2? Pythagorean, exactly right. We used Pythagorean theorem to come up with those. So I'm just going to list wire 1. Wire 1, if you recall, would have been the square root of, would have been 28 squared plus 30 minus x squared. And wire 2 would have been square root of 12 squared plus x squared. Okay, so here we've got, so the wire is going to be, the whole wire would be the square root of 28 squared plus 30 minus x squared plus the square root of 12 squared plus x squared. Okay, so I'm going to pause there for a second and make sure y'all catch up. So I hope you can tell from how crazy that formula looks, that would be really hard to do by hand. This one they would give us a calculator for. Actually 3 and 4, both of those we're going to use a calculator. So we're going to go through some calculator input. When we have a calculator, here's the danger. When we have a calculator, sometimes we are tempted to not write down many things. So we're going to talk about what is the minimum that you need to write down. Okay, first off, you have to write down the formula W. That's like non-negotiable. This is going to be like an optimization problem, right? So we need to find our critical numbers. So also this will have endpoints. So we'll talk about the endpoints in a moment, but I want to talk about the critical numbers. How do we find critical numbers? What do? We take the we take the derivative. So we need to write that down. We don't need to actually write the equation of the derivative down, but we need to write W prime equals 0. That's what we need to write. Okay, and we're going to go to our calculator and we're going to accomplish it. Our calculator is going to do that for us. Okay, you don't have to show the equation of the derivative. You just need to set it equal to 0 and say, okay, so here we go. So let's pull up are we good? Everybody good? Okay, so let's pull up our calculator. and I'm going to do a calculator page. Okay. Now we called this equation W, so I'm going to, in a moment, I'm going to store it as W of X, but let's type it in first. So we've got, what do we have? We've got the square root of, we've got, that's weird, 28 squared. What was it? Plus, then parentheses, 30 minus X. Squared. I don't know why it gave me two parentheses, but okay. All right, so that was our first one. Then plus, then we've got our other radical, which was 12 squared. And I'm not going to actually do that in my head, 28 squared or 12 squared, because I would surely make a mistake. I'm just going to let the calculator do all of it. And then X squared. Okay. So I'm going to store it, and we did this the other day, if you recall. We practiced storing our equations. So I'm just going to do, control. We're going to store this, and I'm going to store it, since we called it W, I'm going to store it as W of X. Okay, so it's sitting there. Are we okay? Now what I'm going to do is I'm going to ask the calculator to find the derivative. Okay, so I'm going to go to this little button right here. See, it's red. Everybody with me? I'm going to the button. I'm going to do the derivative. This is the first derivative. Okay, we've got an X there. Okay, it's going a little crazy. Then this is, I'm going to do the derivative of W, right? And I'm going to get that by, well, there's a couple places I could get it. I'm going to get it from here. There's my W. W of X, and I'm going to store it. Now I'm going to store it as W1 of X, like first derivative, like W1 of X. That's what I'm going to do. Okay, are we okay? So it's there. Now if I don't trust it, and maybe, just for fun, maybe I want to look at the derivative, I could do that. You could just type in W1, of X, and just hit enter, and it'll give it to you. Now that's what we would have gotten if we did it by hand, which is, okay, so it might be fun, but probably not, right? Those are some big numbers. Probably not. So, okay, so we've got our function in there, we've got our derivative. What do we want to do? We want to do what with the derivative? We want to set it equal to 0, right? Okay, you're going to be so proud of me. I actually practiced using the solver just for y'all, because the solver creeps me out, but I practiced it, right? It really does. I'm sorry. I must have been burned in the past with the solver. I don't know. I have. So I practiced it. I used to use 84, and the solver in there is just not nice. And it made me have a wrong answer before, so I'm like, not doing that anymore. I just graph it usually, but we're going out on a limb here. I'm going out on a limb here. We're just gonna hit solve, and there's probably another way to get to solve. I don't really know, but it's fine. Solve, and then what do we want? We want W. We were setting the first derivative equal to 0, right? First derivative. So we want to get that first derivative of X. We want it to be equal to 0. Where's my equal? There. And we want it to do X. There we go. We want it to do X. Okay, do we look good at my solver, people? Do we look good? Okay, good. All right, very good. And it's 9. That's nice, right? That's so very nice. Yay! We used the solver. All right, so let's go to our document we found. So we want to say W prime equals 0 at X equals 9. That's really all the work that you need to show, but you do have to say W prime equals 0. That's kind of a thing. They give you a point for that, so you do need to show that. So let's start our candidate. So we've got X and what do we have? W. Okay, so we know that 9 is a candidate. Now I want you to think about, so sometimes finding the endpoints is a little challenging. So what I want you to think about is which variable that we're using. We're using X, right? We're using X. So we want to know what is the biggest X and the smallest X that would work, like in our circumstance, in the circumstance. So X could be 0, right? And this wire could go all the way to that, this piece. Or X could be 30. You with me? So those would be my endpoints. They would be 0 or 30. Now remember, let's remind ourselves, what do we do with these numbers? Where are we going to put them back in? Which equation are we going to put these candidates in? The original, in the original, right? Because we want to know, we're trying to figure out what is the, what are we doing here? We're doing least amount of wire, so we're minimizing. We want to know the smallest. So that's where we go back to our calculator. Okay, so we're going to do W. So remember, it's the original one, W of 0. And I'm going to put a decimal there because I don't want a crazy answer. I just want decimal. So 53.037. So let's write that down. Come on. There we go. So 0 was 53.037. Then let's find W of 9. So here we go. So W of 9 would be, no, then it didn't like that. Okay, we'll do it again. So W of 9 is 50. Oh, that one looks promising. So that was 50. That's the winner so far. We want a minimize, so the smallest. And the last one we want to check is W of 30. So W of 30. Okay, little thing. And that is 60.311. Okay, so 60.311. So this one is our minimum. So let's see how we need to write our answer. We're going to repeat theirs. Where should the stake be placed? Where should the stake be placed to use the least amount of wire? So that means X would be 9. So now it's asking where should we place it? So we should place it 9 feet. Right, 9 feet from the side with the 12-foot high tower. So we'll just say the word. So the stake should be placed 9 feet from the 12-foot wall. Do they call it a wall or a tower? I don't remember. They call it a tower. 12-foot tower. All right, and there is our second complete optimization problem. How are we doing? Okay, we got one more. And these, let's just look at this other one. Particle motion. Oh, I know y'all missed that. A particle is traveling along the x-axis. So let's think about this concept. It's just going like this, back and forth, right? Traveling along the x-axis. And its position from the origin can be modeled by this x of t, where x is in centimeters and t is in seconds. Okay, great. We want to find when the particle is farthest to the right. Farthest to the right. Are we wanting to minimize or maximize? We want to maximize. We want to be farthest to the right. And what equation do we have that models the position? They gave us one, right? That tells us where it is, but we want to be farthest to the right. So what do you think we need to do? Can we do that with just the position? No, we need to find the velocity, right? We need to find the velocity set equal to 0 and do candidates test. Yay. Here we go. So let's go ahead and do this part by hand for fun. So v of t, it's just power rule, it's good practice. So 3t squared minus, let's see, what is that? 30t plus 72. Let's go ahead and set it equal to 0. And you know, I don't like, what's that? So if we want to be farthest to the right, which is a position, right? Which equation measures going right or left? How do we even know if we're going right or left? The velocity. Velocity gives us the direction, right? It tells us which way we're going. And so if we want to go to the right, let's think about this in terms of the x-axis. If I'm going to the right, am I going to want a big value or a small value? Big, right? Because the farther you go right, the bigger the number is. So I'm going right. I want a big number. I want a maximum. Okay, so we need to find the first derivative so that we can do a sign chart and find our critical numbers. Yes, ma'am? 10. Oh, yeah, thank you. All right, here we go. So I don't like big numbers, so I would just take the 3 out. So now let's, because, you know, numbers are hard, right? Coming from a calculus teacher, right? Okay, so let's see. We need to, back sign's positive. What do we have? 4 and 6. Yep. So we've got t is 4 and t is 6. Okay, so those are our critical numbers. Let's do our, of course, we're optimization, so we're candidates test. So I've got t and I've got x of t. Okay, that's what we're looking at. So I've got a 4 and a 6. Those are my critical numbers. And they also gave us this information. We want to be on the time interval from 3 to 9. So I've got all those numbers to check. Okay, again, candidates test. Those are my candidates, 4 and 6. And the endpoints 3 and 9. Where am I going to plug those into? The original. So it would be to my advantage to put the original in my calculator. Okay, so, and I have too much stuff going on my calculator, so I'm just going to go to a new thing. Okay, here we go. So let's type in, and you just use the x. The calculator doesn't really care. Just use, what is it, x cubed. And then what is that? Minus 15 x squared. And then plus 72x. And then what is it? Minus 9. Okay, now I don't want to store this as x. That's really not a good idea. I want to store it as something else. So I don't know, pick a letter for me. What do we want to store it as? T. Sounds great. Let's store it as t. So I'm storing it as t of x. I made the mistake to just try to store it as t, and the calculator does not like that. You have to put it in function notation. Okay, there we go. It's there. So now we need what? We need t of 3. We need to find that number. T of 3 is 99. We need t of 4. I'm going to use the calculator to get all those numbers, and then we're going to go to our chart. Then we want t of 6. We want t of 6. And then we want t of 9. I did 6 twice, who knows why. T of 9. Okay, there's all of our numbers. Okay, so let's transfer them into our table. And we're looking for the farthest to the right. So who looks like the winner here? T of 9 looks like the winner here. So let's go farthest to the right. So let's just write our numbers in. That was what? That was 99. 4 was 103. 6 was 99, and 9 was 153. So the winner is 9. And again, we need to look at the words they're using. We need to use the same words. So That's farthest to the right. Farthest to the right at, and they want to know when at t equals 9. And if there's units, you have to put them seconds. Okay. How are we doing? One more part. So we want same interval. Notice they wrote on the same interval, so we're still dealing with 3 to 9. Okay, what is the particle's maximum speed? That's weird. Do we remember what speed is? Speed equals, and well, you might not remember. I think it's on the formula chart. Pretty sure it is. Absolute value of v of t is speed. It's the absolute value of v of t, that's speed. We'll just write this down so we keep in mind. So if I want, this is kind of like asking for maximum velocity, but of course in absolute value form. So when I wanted maximum position, how did I find my critical numbers? What equation did I use? I used velocity, the first derivative, right? Well, if I want to find maximum velocity, what equation am I going to use to get my critical numbers? Ideas? You're all like, no way. Okay, so let's think about this for a second. I just want to make sure because it's really important. If we are finding farthest position, which is the x of t, we use the first derivative or velocity. If we are looking for maximum speed, which comes from v of t, we need to use the second derivative, a of t, to get our critical numbers. We always use the derivative of the equation that we're focused on. You with me? So I've got to find a of t, and then I'm going to set it equal to 0 and do candidate's test again. All right, so let's go for that. So we'll call it a v prime of t. Or you can call it a of t. It doesn't matter. Either is fine. So that would be, what, 6t minus 30. So we set it equal to 0. And we get 5. Okay. So here we go. We're going to look at t and v prime, v of t, not v prime, because we're doing candidate's test. Right, so I need 3 and then 5 and then 9. Okay, so I'm going to plug those numbers into velocity. Everybody okay? Yes. Okay, so let's go back to our calculator. So I actually don't have velocity in here. What did we do? We have t of x in here. Let's go ahead and make the calculator do, I mean we already have it. We have two choices. We can make the calculator calculate it for us, or we can input again. It doesn't really matter to me. Why not? Let's make the calculator do its job, right? So here we go. So the derivative of, the derivative of, we wanted t of x. Since I need a bunch of values, I'm going to store it. So control store, we'll call it t1 of x. Okay, so here we go. So we're going to pull this up. So we need what numbers? We need the first derivative, or at where? We need it at 3. And that gives me 9. We need it at 5. Negative 3. We're going to talk about that in a moment as soon as I put it in the table. And then we need it at 9. Okay, so let's copy those numbers into our document. So 3 was 9, 5 was negative 3, and 9 was 45. Now, I want to talk about this negative one. This is in velocity. speed is the absolute value of velocity. So if this was like negative 300, this would have been the maximum speed, right? Because it's absolute value of negative 300, which is 300. Now, it's not. I'm just saying we don't need to discount it because it's negative because, again, speed is the absolute value of velocity. These numbers are not in absolute value form. So it's 45. So let's, again, see how we want to word it. So we would say maximum speed is 45. Let's see, our units weren't they centimeters? Okay, thank you. So they were centimeters per second. Oh, goodness gracious. All right.